Lesson 69, we get into simplifying complex expressions. We've worked with complex numbers before, so let's start with a little review. Complex number, again, is made up from a real component and an imaginary component. If we take a look at example 1a, the example 3 plus 4i, we would consider the 3 to be our real part and our 4 to be our imaginary part. And one of the things we can do with complex numbers is we can graph them on our complex plane. Now if we take a look at this complex plane, notice we have our two axes. It looks like our x and our y, but notice we've renamed them. The x-axis is now going to represent our real component, and the y-axis is going to represent our imaginary component. So if we start with graphing the very first one, 3 plus 4i, we're going to march 3 units to the right on the real axis, and then we're going to march up 4 units on the imaginary, getting us to this point approximately right here. And let's call that point A. Let's take a look at B. Negative 2 minus 3i. Negative 2 means we're going to march 2 units to the left and down 3 units. Therefore, we are going to arrive at this point right here. Let's call it B. Let's take a look at C. Negative 4i. Now notice with negative 4i we don't have a real component, so we're going to stay right on the y-axis and we're just going to go straight down 4 units. And there's going to be our negative 4i. And the last one, negative 2, here we have just the real part, so we're going to march 2 units to the left and we're going to stay right on that x-axis. And that's how we graph these complex numbers. The real numbers are your x values and your imaginary numbers are your y values. Another thing that we can do with complex numbers is find the absolute value of a complex number. The formula that we're going to use. Suppose we have some number in the form a plus bi. We have our real and our imaginary. How do we find the absolute value? Well, we're basically finding the distance from the origin to that point, a plus bi. So we're actually going to be using the Pythagorean theorem where we use the real part and the imaginary part. If you would like more explanation on that, don't be afraid to turn back to your book on page 489, and they show you a graph of that point a plus bi being plotted and the distance from the origin to that point using our Pythagorean theorem. So for example number 2, let's go ahead and find the absolute value of the number, negative 2 minus 3i. We start with our formula. Let's go back to it. The square root of a squared plus b squared. It's as simple as that. We are going to plug in our a value, which is negative 2, and then our b value, which is just simply negative 3. Now, a lot of students in the past will try to plug in that I. Just understand, we don't need to use the I for the absolute value. We just plug in negative 2 as well as negative 3. We keep simplifying to get 4 and 9, and obviously we come up with the square root of 13. Not a perfect square, can't reduce any further. That's all we need to have there. The third thing that we can do in lesson 69 with complex expressions is we can multiply these guys. Now remember, when we multiply, we always want to write our answers in the form of a plus bi. So let's start with the first one. Negative 4i times the quantity 7 plus 3i. When we multiply, just like you would expect, we're going to start by distributing. We're going to take that negative 4i and multiply it by the 7. And in doing so, we are going to get negative 28i. And now we need to go ahead and distribute to the second term. So let's go ahead and do that. Negative 4 times negative 3 is going to get us negative 12. And then I times I is going to get us I squared. Now we can simplify a little bit further. The negative 28i we can't do anything with, but recall I squared is equivalent to negative 1. So when we do that, we get negative 28i plus 12. And lastly, we do want to be in that form of a plus bi. We recognize that 12 is our a, that's our real part. Negative 28i is our imaginary part. So there we are in the form a plus bi. Let's take a look at b. As you would expect, we want to FOIL here. So 5 times 6 will get us 30. 5 times negative 2i will get us negative 10i. 4i times 6 will get us plus 24i. And then lastly, positive 4i times negative 2i will get us negative 8i squared. Now let's see if we can simplify this a little bit. 30 we can't do anything with. If we take a look at these middle two terms, negative 10i and plus 24i, yes, we can collect those to get a positive 14i. And then lastly, if we take a look at the negative 8i squared, again, the I squared is equivalent to negative 1. Therefore, if we keep going, that becomes a positive 8. And lastly, if we put it into form, 30 and 8 will get us 38 plus 14i. The last thing we can do is divide. We start with our 3 divided by 6 plus I times the square root of 5. Now, if you would imagine, we don't want the I or the radical of 5 down in the denominator, so we essentially want to rationalize this complex number. We're going to start by multiplying both top and bottom, if you would guess, by 6 minus I squared 5. It's our conjugate. It's the exact same concept that we used when we were dealing with radicals. We keep both terms the same, except we change the sign in between. So there they are. Fraction bar acts as a grouping symbol. Now when I multiply these guys, I'm actually just going to leave the 3 out in front. I'm not going to distribute. Let's leave it like that for now. And now let's go ahead and FOIL our denominators. Now if you recall, with the conjugates, we don't need to actually do the O and the I of the FOIL process. All we have to do is do the first and the last terms. 6 times 6 will get us 36. And now again, those middle terms will cancel out, so let's just go to the last terms. I times the square root of 5 times negative I times square root of 5. Well, 5 times 5, we know our answer needs to be negative. Square root of 5 times square root of 5 will get us 5, and then I times I is I squared. Let's keep going. 3 times the quantity 6 minus I squared is 5 over 36 minus 5I squared. 36 minus 5 I squared again is negative 1. Now I do want to go ahead and distribute that 3. All over. Negative 5 times negative 1 will get us a positive 5. I'm going to combine steps here. 36 plus 5 will get us 41. I think you're all fine with that. And lastly, let's go ahead and get it into form. 18 over 41 is going to be our A, minus 3 square roots of 5 over 41 is going to be our B times I. That's our form, A plus or minus BI. Last one, we want to take 4 plus I and divide it by 6I. So 4 plus I divided by 6I. And as you would imagine, again, we don't want that I in the denominator. So, just like we've done in the past, we're going to start by multiplying both sides by 6I. And in doing so, we come up with the following. When we distribute, fraction bar acts as a grouping symbol. We get 24I plus 6I squared. Down below, 6 times 6 is 36, I squared. So let's clean this up a little bit. We get 24I plus 6 times negative 1 over 36 times negative 1. So 24I minus 6 over negative 36. Now to get this into the form, I'm actually going to bring my 6 out in front. And my plus 24I behind. And again, I distributed. I put the 36 underneath each term, and when we simplify, notice those two negatives cancel each other out. That looks a lot better. And then 24 over 36 reduces down to 2/3. So negative 2/3 I. If you wanted to, you could just go 1/6 minus 2/3 I. Same thing. There's your answer. Practice problems that I'd like you to try from the lesson practice on page 492. Problems A, C, E, H, I, and M. Once you complete those 6 problems, you can check the teacher's edition and then move on to lesson 70.